Okay, so in the previous video, we analyzed the pressure drop for a laminar flow. And the criterion for a laminar flow is if the Reynolds number based on the diameter of the tube is less than 2,300. Now, we're going to analyze or go over a turbulent flow in pipes, and we'll discuss turbulent boundary layers in a bit more detail in Chapter 9, but in most practical cases, you have turbulent flow. Because if you actually evaluate the criterion for a lot of cases, for the Reynolds number being less than 2,300, the flow rates are often way too low to be practical for most anything, with the exception of a very few specialized applications. Like your blood flow in your blood vessels tends to be laminar because your heart has to work a lot less hard to move the fluid around than if the flow is turbulent. And now the turbulence is the same turbulence that if you've flown on a turbulent skies and how the plane jiggles around. Well, that's the same phenomena that is causing that causes turbulence in pipe. And turbulence is characterized by chaotic, unsteady, strictly speaking, flow. So, in our laminar flow, recall that you can analyze Navier-Stokes exactly, and the streamlines are perfectly flat and straight lines. So that's laminar, and the velocity profile, as we derived, is perfectly parabolic. But turbulent flow, on the other hand, the streamlines are now chaotic. That is, they're kind of going all over the place. Okay, and these chaotic, jiggly streamlines are functions of time. That is, this streamline up here, it'll wiggle around, it will move around, and it will change with time. So strictly speaking, the flow in a turbulent duct flow or in a turbulent pipe is unsteady, and I'll show you some experiments and some direct numerical simulations of turbulent boundary layer flows in Chapter 9 when we briefly discuss boundary layers. And this will become more evident at that point. And so, and in a turbulent flow, you can derive a mean quantity, and it turns out that on average, the mean velocity profile is actually much more flat. Okay, and so for turbulent flow, the peak velocity at the center line of the channel is actually not that much more than the average velocity in the channel, and so the mean velocity profile looks something like this most of the time. Now, the true velocity profile as a function of time could look something like that at one time instance. Then at another time instance, it could look something like this. Then at another time instance, it could look something like this. And at another time instance, it could look something like this. But if you take all of these instantaneous sort of profiles that I superimposed, you wind up with an average profile that will look something like that. Okay, and that average will, and even though the details of the flow with all these little jiggles are unsteady, the mean properties of the flow are steady. Okay, and so we're going to analyze these steady turbulent flows. Now, even though the turbulence itself means that the details are always unsteady, and if you want to solve a turbulent flow directly, you can use the Navier-Stokes equations that we derived, but you need to solve them in their unsteady version. You cannot solve them steady. There are techniques for solving steady turbulent flows, and that is way beyond the scope of this class. Okay, and so the flow in a pipe is turbulent if RED is greater than 2300 for most designs, or if it's very carefully designed, you can have laminar flow up to a Reynolds number of 100,000. And so the classic case, there are some experiments done by Osborne Reynolds where he had just a tank filling a pipe, and in this case here the streamlines became turbulent almost right away. And in another experiment, he did it up to a Reynolds number of 100,000, and he very carefully contoured the flow, and then the streamlines just nicely hugged the contours, and so the streamlines, it took a lot more for the flow, for the nice laminar flow to devolve into a chaotic turbulent flow. Okay, and there are specific fluid mechanical reasons for why this case with sharp edges and things like that are more prone to turbulence, and that has to do with the fact that if we look at the flow as it goes around this corner here, the streamline, the fluid elements have some inertia to them. So rather than just turning and making a 90-degree corner like that, they can't do that because they have inertia. So what they do then is they basically overshoot it, then turn and then go back around. In this region here, there will be a vortex that will actually of spinning fluid right there, and that's a vortex. And this region here is called the vena contracta. And we'll discuss those a little bit more when we discuss minor losses, because it takes a lot of some power to actually spin the fluid in this vena contracta, and so there's actually a significant pressure drop as the flow goes down and around this corner here. And so as opposed to if you smoothly contoured the inlet. And so and this so-called trips the boundary layer into turbulence. Okay, now if we consider a pipe flow, and I'm going to have a device called a hot wire anemometer, and I'm going to measure U. Well, if the flow, I'm going to measure U as a function of time. If it's laminar, it'll be perfectly straight. So this is laminar. And if it's turbulent, it'll be bumpy and jiggly. But despite the bumps and the jiggles, there will be a mean velocity profile, or a mean velocity. I'll call that U bar. And then there will be a fluctuating velocity, and I'll call this U prime. And so for a turbulent flow, U equals the mean plus this little fluctuating component here. Okay? And essentially, there are a lot of turbulent analysis techniques where you basically use this definition of U, substitute them into the flow equations, and then average them out. And I'm not going to get into that in this class. If you're interested, the book discusses that in somewhat more detail than what I'm going to go into. And there are a lot of really good books that discuss how to do that. And so this would be the mean, and this would be the fluctuating. Okay, and it turns out that for a turbulent flow, the shear stress is equal to mu times the du dy, where if we have a channel or a pipe, we can measure y as the distance from the wall. And so y is just equal to mu times the slope of the mean velocity profile minus the so-called Reynolds stress. And that's y, and that's rho times u prime v prime bar. And I'm not going to get into what this is that in a turbulent flow, there are always fluctuations of the velocity in all three directions. Even if v bar equals 0 and w bar equals 0, v prime and w prime are not equal to 0 in a turbulent flow. Okay, and so this term here, you could consider this tau laminar, and this is tau turbulent. Okay, and there is no exact theory for this. And it's really analyzing this. These turbulent flows are what make fluid mechanics such a difficult field. And in fact, turbulence is actually one of the greatest unsolved scientific mysteries to the state to where you still have physicists working on it. It's at that level of being unsolved. And now there are lots of ways to model tau turbulence, or the turbulent shear stress, and it is sometimes modeled with tau turb equals rho times some length scale squared times du bar dy, the absolute value of that, times du bar dy. And this here is called a turbulent viscosity. And this here is called a mixing length. Okay, and I'm not going to get into the details of what that is at this point, but just know that for a turbulent flow, there is a shear stress just due to the mean velocity profile, like this. And there is a shear stress, due to the random fluctuations of the turbulent flow. Okay, and so just the random jiggliness of the flow induces a so-called turbulent shear stress. And that needs to be modeled in those, and that that's actually a very difficult flow field, and people spend their careers trying to model that better and better and better. Okay? But now what's interesting is that the turbulent viscosity is not equal to a constant, but it's a function of the flow details. Okay? So the turbulent of viscosity is not a number you pick out the back of a book. It is dependent upon the flow field, and that's another reason that turbulence is really difficult to analyze. And this is the simplest turbulence model there is, because even though fundamentally the turbulent shear stress depends on the jiggliness and the random fluctuations of the velocity field in the pipe, you are modeling those through rho times a length scale squared times the absolute value of the mean velocity gradient, and so the flow, and so the sharper the gradient, the higher the turbulent shear stress. And so this really increases the viscosity near the wall. So if I draw the tube, and just for reference I'll draw a laminar velocity profile. Well, for turbulent, if the flow is turbulent, the turbulent viscosity would be next to zero here and very high over here. And so what you wind up with then is intense shear stress, is an enhanced shear stress right at the wall here, which increases tau wall, which increases the pressure drop. And the effect on the mean velocity profile is that it is very flat for most of the pipe, except for near the walls. Okay, where it basically it is basically nearly constant for most of the channel or the pipe, and then it takes a severe nosedive once it gets close to the wall. And this is du bar, dy is, or the absolute value of that is very, very high than the absolute value of du, I'll rewrite that, of du dy for laminar. Okay, and so that means that the shear stress at the wall here for a turbulent flow is very, very, very high. And empirically, you can say that U bar equals U max, which is at the center line, times 1 minus R over capital R, where capital R is the outer diameter of the tube, raised to the 1 over N. And I'm going to move this diagram here. Oh, come on. Okay, well, I guess I will move under this diagram for the time being. It's being stubborn. Okay, forget it. Where N is usually 7. So if you recall back to quiz 4, I had you analyze a channel that had this, that had a profile like this, with the 1/7 profile, and it wasn't Ryan being nasty. It was actually analyzing a mean turbulent velocity profile. Okay, and this is N is usually a 1/7, and 4. I'll move back up to that chart once we need it. U average over U max for a turbulent flow equals 2 N squared over N plus 1 over 2n plus 1. If you just go through and analyze the maximum value at the center line, and you analyze the average value, you wind up with this. And this for n equals 7, which is called Prandtl's 1/7 law, or 1/7 profile. For n equals 7, this equals 0.87. Okay, and so recall that for laminar flow, this was 0.5 for laminar. Okay, and the other thing, so aside from having a very flat velocity profile, the turbulent flow is very sensitive to the surface conditions. So turbulent flow is sensitive to surface roughness. Okay, so if I have a pipe here, and either due to machining marks, or I get some crud that sticks to the inner wall of the pipe, and I have a bunch of little peaks and valleys like over here, what's going to happen is that the streamlines close to the wall are going to be affected by all these little bumps. Okay, and basically what you'll wind up with is instead of the flow just going up and over them nicely, in a turbulent flow what will happen is they'll actually is that the flow will actually be substantially influenced by all these little peaks and valleys, and then you'll get all these little like all these little vortexes in these little valleys here, and it takes a lot of energy to basically run those, and so to basically cause the flow to spin in basically all these little valleys. And for a turbulent flow, these can have a substantial influence on the pressure drop. And there's also more fundamental reasons why surface roughness affects a turbulent flow. But for a laminar flow, the flow has a lot lower momentum, so it actually has time to turn and actually hug all these little valleys. And so for a laminar flow, the surface roughness does not have an effect. Okay, and so for a laminar flow, you can treat the surface roughness of the tube as being smooth. Now again, that's at some point, if the surface roughness becomes, cartoonishly huge, like you have a little spike sticking out there, well, that's no longer surface roughness. That's an actual feature in the pipe, and of course that's going to influence the flow. We're talking very small little bumps on the surface. And so now we're going to characterize the height of these surface roughness bumps with a height called epsilon. And that's the surface roughness. And that's the characteristic height of the surface roughness. Okay, and so now the major losses for turbulent flow, which is the Moody chart, for laminar flow, we found that the Darcy friction factor, F lam, was just 64 over RE d, and delta P for the major flow losses was F times L over d times the dynamic pressure. Okay, and that's really bad squared, so we'll fix that. So how about turbulent flow? Well, we found that delta P in the laminar flow is caused by tau wall, okay, which depends on the flow. On the flow, and it'll depend on the roughness, etc. And so delta P in general will be equal to, I'll just say phi, I'm not going to call it F because F is the Darcy friction factor, of U average, how fast the flow is moving, the diameter of the tube, of the length, the surface roughness, the viscosity, and the density. And so these are properties of the fluid. This is surface roughness. This is the length of the pipe. This is the diameter. And this is the mean flow. Okay, and so if you use Buckingham Pi, you have delta P over 1/2 rho U averaged squared, where again this 1/2 was put there to turn what actually comes out of Buckingham Pi into the dynamic pressure. That equals some function of rho U average d over mu, L over d, and epsilon over d. Okay, and epsilon over d is called the relative roughness. And it's just the ratio of the height of these roughness of the surface roughness to the overall pipe diameter d. Okay. And so, however, this parameter here is just the Reynolds number. So, however, for a turbulent flow, dP dx is still constant. Okay, so if dP dx is equal to a constant, this means that it is equal to delta P over L. So if you have a pipe and the pressure in it is like in the pressure in that pipe, or in the dP dx is essentially constant, we can define a P1, P2, and P1 minus P2 equals delta P, and the length between them is L. Okay, and so that's just equal to the slope, and so dP dx is equal to delta P over L. And so this implies that delta P is just equal to L times dP dx. So this means that delta P is proportional to L. So what that means, what we can then conclude, is that in the Buckingham Pi Theorem, it says that the pressure drop scaled by the dynamic pressure is equal to some function of the Reynolds number, time, and the length over diameter of the pipe, and the relative roughness. Now, what this result's saying, because we know empirically that dp dx is constant, that means that delta P is proportional to L. And so that implies that this function here is actually is actually proportional to L over D. So thus, delta P over 1/2 rho U averaged squared is equal to L over D times phi of RED and epsilon over D. Okay? Because we know that delta P has to be proportional to L. And the dimensionless parameter that contains L is the second one here. So it needs to be proportional to this pi group over here. Okay? So now we know this, or delta P equals phi RED epsilon over D times L over D times rho U averaged squared over 2. Okay, and this phi is just F, the Darcy friction factor. Okay, and so that's why, and of course we only know to do this because we carefully analyzed the laminar case, and we're trying to draw analogies to the laminar case basically wherever possible. So using our results from a laminar flow and extending the Buckingham Pi analysis to account for extra features that are important for turbulent flow, we see that delta P is still F L over D times the dynamic pressure. Okay, and so now how do we get F? So F laminar equals 64 over RED as we derived, but how about F turbulent? Well, for that, this F is obtained empirically and displayed on the Moody chart, which was that stubborn chart that I could not get it to move earlier. Okay, and so that's for F turbulent. And so I'm gonna scooch back up to that stubborn immobile diagram, which is way up here. And so this here is the Moody diagram, and there's one in the back cover of your book. And so this here is from the Moody chart wiki. It's actually a very nice diagram, and this contains the laminar section. And so for laminar flow here, so on the x-axis we have the Reynolds number based on the pipe diameter, and on the y-axis we have the Darcy friction factor, F. Okay, and so in the laminar section here we have 64 over RED, and they truncate it at about 2300, as you see here. And note, if you choose to use the Darcy or the Moody diagram, note that the x and the y-axes are on a log scale, so be very, very careful when you read it. Okay? And so, and off to the far right, we have a region that's called complete turbulence, and this is called fully turbulent flow. And in this region, phi is just equal to a function of the relative roughness. Okay, because the x-axis is the Reynolds number, and if we're far enough, and if the Reynolds number is high enough, essentially you can see all these different lines here corresponds to different values of the relative roughness. Okay, so how you read this diagram, say you have an epsilon, which you can find on this little table here, and it's also on the table in the book, and when I go over the examples I'll explain this in more detail. But you compute epsilon over d, and then after you compute epsilon over d, that basically tells you which of these lines to read from. So let's say epsilon over d is 0.002. Then we compute RED. And so if we have RED equals 10 to the 6, so say we have an RED of 1 million and a relative roughness of 2 to the minus 3. So basically, we read this line here, this blue line, and we follow it until we get 10 to the 6, which would be right here. And so that would correspond to an F value of about, say 2.02 0.022, something like that. Okay, or if the relative roughness was say 0.001 and the Reynolds number was say 10 to the 5th, we would follow this 0.001 line here and follow it up till we hit 10 to the 5th, which would be right about here. Okay, and so that's basically how you read it. Is that the x-axis is the Reynolds number, and there are families of curves that correspond to the relative roughness. Okay, and so however, you notice that if the Reynolds number is very high and or the tube is very rough, the influence of the surface and the influence of the surface roughness actually overwhelms everything else, and the Darcy friction factor is a function only of the relative roughness, because these lines are almost perfectly flat. And in this region here, it is not fully turbulent, and the Darcy friction factor is a function of both the Reynolds number and the relative pipe roughness. Okay, and this region here is called transitional turbulence. We're not going to get into transitional turbulence in this class, but there's no such thing as a state that's halfway turbulent and halfway laminar. At various times, the flow is either laminar or turbulent. It is one or the other. And so if you have a transitional turbulent flow that's here, in some locations the Darcy friction factor will be here, and where it's laminar, and in regions where the flow is turbulent, it will basically jump up to there. If you're designing something, you really do not want your design to be in this regime here. You either want it to be over here, where it's always laminar, or over here somewhere where it is always turbulent. You do not want to be in a transitional regime. If it's transitional, you want to be in there for a very small time, or for a very small short section of your device. Okay. And so there is another way to compute the Darcy friction factor. So how is F turbulence calculated? Because that Moody chart had some very nice smooth curves, and it is an empirical chart, and certainly they didn't do an infinite number of experiments to fully characterize that chart. Well, a guy by the name of Colebrook actually took a lot of empirical data and actually did a curve fit to it. And the turbulent portion of that diagram is computed using the Colebrook equation. Okay, and this is just a correlation to lots of data. But this Colebrook equation, which I'm gonna scribble down here, which is 1 over the square root of F, and this is turbulent. It does not work for laminar flow, equals -2 times the log base 10 of the relative roughness epsilon over d divided by 3.7 plus 2.51 over RED square root of F. Okay, and so this is the Colebrook equation. And this Colebrook equation is actually the one that is used to compute the relative, or to compute to basically make the lines in the turbulent portion of the Moody diagram. However, this is an implicit equation, and that is you cannot solve it directly and analytically to find F. There is no way to do that. And so this is for, and also I'll just say for turbulent flow in pipes. Okay, and so to solve, you can use Wolfram, MATLAB, Mathematica, or you iterate. And so I will show this iteration in Wolfram Alpha on some examples. Then I'll just describe how to do the iteration, because this actually this equation actually iterates very, very nicely. It's a very well-behaved equation. It's not like some of the nasty, evil equations that you might have had to deal with in numerical methods. To solve, you can iterate. So the steps for that are 1, get RED and the relative roughness. 2, guess F. 3, compute F new equals this equation here, and I'm going to solve this for this F here. Okay, and so that will equal to 1 over 4 times 1 over log 10 of epsilon over d over 3.7 plus 2.51 over RED square root of F guess squared. Okay. And so basically, you guess F, you put that into this equation here, and that gives you a new F. And essentially how I got this was I took this equation here, divided it, inverted it by dividing it by 1, and then I squared it. And if you do that, you get this equation here. Okay, and then 4, you have a criterion that if the absolute value of F new minus F guess is less than some error tolerance, which you need to specify, F equals F nu. Okay? And if you did not meet the tolerance, else F nu, and then you stop after that. Else F guess equals F nu, and you go to step 3. Okay. And so it's an iterative procedure. It's very easy to code up, and it works really fast. You don't need to do anything fancy with Newton-Raphson or anything like that. You can just basically basically march it along using this what's called fixed point iteration technique here. But for turbulent flow, F guess for the first time of 0.1 usually works well and converges in a few iterations.